Hi, my name is Nick. What's your name?
My name is Bogdan.
Who do you work for? Who's your PI?
I'm a postdoctoral researcher here, and I work with Professor Stepanov.
Okay. And I guess I got a couple questions for you today. So
Yeah.
what's your main area of expertise?
My main field of expertise is two-dimensional materials
Okay.
and scanning probe methods.
So for someone who doesn't know what those are, how would you explain that to someone?
Yeah, for the sake of a broad audience, I think I need to give a bit of background
Oh yeah.
on these materials. So in 2004, Andrei Gaim and Konstantin Novoselov discovered and studied graphene. Graphene is mono-layer sheets of carbon atoms.
Okay.
So you can basically peel off very thin layer from graphite, and you will have graphene.
So basically, it's two-dimensional graphite.
Yes, it's two-dimensional graphite.
Okay.
And people very quickly realized that this is pretty fascinating materials because, as Gang and Novoselov showed, in these materials, dispersion of electrons is linear.
Okay.
Which basically means that they behave as if they have no mass.
Okay.
So they are massless particles.
Interesting.
So you can describe them with Dirac equation, and basically you can observe relativistic effects in solid state material, which is really nice. But the problem with graphene is that such massless particles, they do not interact much with each other.
Yeah.
And rich and fascinating physics often originates from interactions
Yeah.
between particles. So a couple years later, after discovery of graphene, people realized that you actually can take one graphene sheet and place it on top of each other with small twist angle.
Okay.
And in that case, you will have like two Dirac cones, which
are, for people who don't know what Dirac cone is, what is a Dirac?
Well, it's just relation between energy and momentum. So
Okay.
in graphene, you have a Dirac cone, it's linear dispersion, and basically it means that your particles are massless.
Okay.
So if you have one graphene sheet, you have dispersion like this. But if you have another on top of it with a little twist angle, you have another Dirac cone. And in that case, they hybridate, and you actually can observe a new dispersion. You have a dispersion band here, some band here, and we have flat bands. And flat bands is basically the opposite of Dirac cone.
Okay.
So you just use two sheets of material with massless electrons, and what we get here is so within these bands, mass of electrons is huge.
Yeah.
And interactions are really strong.
Okay.
So now this system becomes very sensitive and very tunable to any distortions, to any additional electron in the system.
Okay.
So basically, so in simple words, when your interactions are so strong,
yep,
you can imagine it as a couple of sites where electrons can sit, and they want to minimize energy. So one electron sits here, one sits here, and one here. If you add one more electron, it wants to sit on site with minimum energy for the whole system.
Okay.
So why it happens? Because they interact with each other. They know everything about each other.
Yeah.
And if you put another electron in the system, it should sit somewhere where energy is minimum, right?
Okay. Yeah.
So, and because of that, you can tune charge carrier density in that system, and you can actually reach the whole variety of fascinating physics.
Okay.
So you can observe ferroelectricity, anomalous quantum Hall effect, superconductivity, some Chern insulating states, topological insulating states, and many, many, many others.
Okay, but I just want to go back to the Dirac current first, because you got here. So this is momentum.
Yes.
So this implies that as like the momentum increases, let's say you're on this curve, your energy would decrease for a while and then go back up, correct?
Well, you have kind of zero.
Okay. Okay, gotcha.
So usually you have like a quadratic behavior.
Yeah.
Because your kinetic energy quadratically proportional to
Yeah.
the momentum.
Mm-hmm.
In case of massless electrons, you have linear dispersion. In flat bands, you increase momentum, but your energy stays the same. Because now it doesn't depend on momentum. It depends only on interaction.
Yeah, so it's like this layout is how.
Yeah. So in that case, your kinetic energy is way lesser than your potential energy, interaction energy.
Okay, that makes sense.
So, and basically today we will be assembling one of these structures.
Okay.
So, I just wanted to say that what is really nice about these structures is that you don't need any fancy machines like molecular beam epitaxy, atomic layer deposition, or other like high vacuum fancy systems.
Okay.
Technically, you can assemble one of these structures at home.
Wow.
Yeah.
How much does that cost me though?
It depends on quality and structure you want to achieve. But yeah, technically you can do it at home.
Okay. Interesting. Yeah. So, is this all the physics you need to know for this, or would let's say I wanted to go let's say I found this really interesting. I wanted to go into I assume I probably need go into grad school for this.
Mm-hmm.
What are some stuff you'd recommend me take to learn more about this, so I could then learn more about this in the future?
Well, I would recommend to learn as much as possible about semiconductor physics and solid state physics.
Okay.
So basically, take some quantum introduction, quantum, and all this stuff.
So quantum and solid states are those are the important classes.
Yeah, but I mean, when you come to the lab, you always face some very specific things.
Yeah.
So basically, your senior colleagues should teach you how to do this.
Yeah. Would you say that your classes that you're taking, would you say they prepare you for lab, or is this just completely different than what you're learning in class?
Well, they give you some theoretical basis of that, but in research you have to do a lot of stuff which is not covered with theoretical problems.
Okay.
I mean, in real life, your structure is not ideal. It's dirty. It has some impurities, and you have to understand how to eliminate these effects.
Gotcha. So, but yeah. So you said you're going to show us how we construct one of those.
Yes.
Okay.
So basically, everything starts with graphene. So this is very old method of fabricating graphene. So you just can put large graphite piece on Scotch tape.
Okay.
Peel it off this
tape,
and then put another Scotch tape on top of it.
So hypothetically, if I have a pencil, could I just pencil on top of Scotch tape and then
yes.
Okay.
There is a chance that you can get graphene.
Okay.
I believe that every time you draw something with pencil, you actually produce a lot of graphene.
Okay.
We don't know.
Yeah.
Right. Okay. So when we can stick this tape to silicon oxide substrates.
Okay.
And when you peel it off, you actually can see that there are some flakes.
Are those pieces of graphene?
Yes.
Okay.
Yes, this is a piece of graphene.
So why does the silicon take off the graphene from the tape? Is that just a resin?
Because of Van der Waals force. So basically, in graphite, only Van der Waals force holds these layers together. So there is no real chemical bonds between layers.
Okay.
So and when you put it in contact with nice, flat, clean surface, the same force can actually peel it off.
Okay.
And here we can see optical image of graphene. This is one atom of carbon here. This is
like 1 pixel is 1 atom?
No, I mean this is monatomic layer. It's
Okay.
1 atom thick.
Oh, okay.
Yeah, and this is quite thick layer.
Okay.
So you can see that the key feature of graphene is that it's transparent.
Okay.
So basically we can see through it. It absorbs only like 3% of light.
Okay.
But bulk sample isn't transparent at all.
Yeah. That's what makes a good pencil light. Yeah.
Because metals are not transparent in general.
Yeah. Mm-hmm.
So, yeah. Okay, and so now we want to pick up one part of that graphene.
Actually, before we do that, I have a question.
Yeah,
so
sure.
we have this nice image here,
Yeah.
and I assume that's coming from this microscope.
Yes, sure.
How is it able to see 1 atom thick layers of something? So.
Because it absorbs some portion of light.
Okay.
So we have basically our silicon oxide also helps us to see, because what we have here. Okay, so we have silicon substrate,
Okay.
and 300 millimeters of silicon oxide.
Okay.
And this silicon oxide works as a like Fabry-Perot resonator.
Okay.
The light comes in, comes out, and we have some interference between these two beams.
Okay.
And if you put something on top of this silicon oxide, then your contrast will be enhanced by this like Fabry-Perot type resonator.
Okay. That's really clever. So.
Yeah, we have the image here, and we can clearly see this area. It's only 1 carbon atom thick.
Okay.
So 0.3 nanometers. Yeah, it's crazy thin. So, and now we want to pick it up.
Okay.
But to do that, we need to use another material, because if I directly pick it up with some polymer,
Mm-hmm.
I will make the surface dirty. I will
Yeah.
contaminate it. I can spoil the whole fascinating physics. So I need to use something atomically flat, clean, nice. So we will be using hexagonal boron nitride.
Okay.
So it's very similar to graphene.
Okay.
In terms of mechanical properties and structure, but it's insulator. It's not.
Okay.
It's not metal. So it's really good insulator, and we can kind of encapsulate graphene between 2 boron nitride layers.
Okay.
And then we can study properties of this twisted graphene layer.
Okay.
So to do that, we need another substrate. So, okay, let me. Yeah, to pick up hexagonal boron nitride, we use so-called stamps. So it's just glass slide with polymethyl disilexane triangle covered with polycarbonate films. So it's just polymer which is sticky and which we can melt to transfer it on target substrate. Okay, so first of all, we need to find good hexagonal boron nitride flake here. So I'm going to find it.
So how do you know what you're looking for?
I just know.
Okay.
So,
Just something that comes with practice.
yeah.
What do the different colors mean on the screen?
They actually correspond to different thickness.
Okay.
Hexagonal boron nitride is transparent.
Okay.
But when it's quite thin, it also works like an interferometer.
Okay.
And depends on thickness, you can observe different colors because you have resonance for different wavelengths.
Yeah.
There are some tricks how to do that, but in general it's quite simple procedure. And also we heat up our substrate.
Okay.
To make interface between HB and hexagonal boron nitride and silicon oxide less sticky.
Okay. So are you doing that? Is there like, how are you heating up? Is it like just the light is heating up there, or is there
No,
like?
it's a resistive heater.
Okay. And presumably that doesn't really do that much to the graphene.
Hmm?
That doesn't like do that much to the
No.
graphene. Okay.
So we're already close to the surface. This is our PDMS triangle, and we are going to see the contact point. It's here.
Okay.
But this part of polymer is already in physical contact with surface.
Okay.
So now we should extend this contact point and reach our plate.
Okay.
So now we can try to pick it up. Go back. So you can see that it actually lost its color. It's
Okay.
not bluish anymore because there is a space between CO2
Okay.
and plate.
Interesting.
So we pick it up.
How precise is that knob on there to move it up and down?
It's quite precise.
Okay.
It's like, I don't know, micrometer scale.
Wow.
So now we can focus on our polymer, and here's our plate.
Okay. That's so cool.
This is nice, clean, atomically flat HBN. So we can use it to pick up our graphene.
Okay.
Now we need to find our graphene again.
So the like little blue box on there, that's the shape of the boron nitride.
Yes.
How, like, did you have to like make that yourself, or do you have a computer program that runs that, or how does that work?
I drew it. I
Yeah.
just drew it.
Okay.
Okay. So now we need align our
Okay.
HBM and our graphene.
I have to wonder because you got that fancy joystick there for how you're controlling it. How much effort do you think it takes to like learn how to actually use one of these?
You can try. You can
Is there a difference between these two?
Yes, it's different directions. It's X and Y.
Okay. That's so cool.
Yeah.
Such a, I don't, I've never seen something like that where you can just like, and I would have thought it'd been super sensitive, but no,
Well,
it's,
you can make it super sensitive.
okay.
Okay.
Whoa.
So now it's super sensitive. We have like a 2 modes, precise and rough.
Gotcha. Okay. That's really cool.
Yeah, I like it.
I don't know how I would have thought about doing like a three-dimensional, but yeah, it's,
We have 3-dimensional joystick in Glowbox. We have not
oh wow.
in inner atmosphere, and it can move all 3.
Wow. So you're just switching between like different kind of lens ideas to try and be able to see both the boron nitride and the graphene layer at once.
Them closer and closer.
Okay. So now we can see the graphene on screen.
Yes. Now we finally can see graphene. So now I move my APM inside this
Okay.
bluish. And now, even if I do not see it, I can note it's over here.
Okay.
And I can slowly check this here. Switch it. Now I kind of can see both.
Okay. Yeah, you can see both. Did you like change the filter color on that or?
It was a comment. I did it too quickly.
Oh, okay. How do you know if you picked it up or not? Okay.
Let's see it anymore.
Yeah.
So now we need to increase 2 dB,
Okay.
1 degree, 1.1 degree.
Okay.
We call it magic angle.
Okay.
Because it gives the most fascinating.
Okay.
Also, I need to know where my graphene is.
Say an area of 400 something micrometers squared.
Yeah.
That's so small.
Yeah, that's tiny.
I think for context, that's probably like that's far smaller than like the area of like a human hair.
Yeah,
Yeah.
definitely. I mean, when you assemble structure, like everything rest is quite easy. You just need to use EVA to fabricate 1 micrometer size contacts, put it in cryostat, cool it down to like below 1 Kelvin, shine it with some fancy lasers, magnetic field, and then maybe, probably, you can observe some.
Well, when you say that, it sounds easy. No, I have some friends taking a like a solid state class, and I've heard a lot of things from them about like trying to do like work at like such a small scale, and I'm very impressed how well you can do it. I definitely could not do it that well. So
Now you can see. Now we are in contact with the second
okay,
sheet, and it's twisted a bit,
okay,
so it should create more red pattern.
okay.
Maybe I can show you. I'm not so good at drawing picture,
Yeah.
so I use Google. So when you have two sheets of graphene, you have small hexagonal lattice.
Okay.
But when you twist it a bit, you actually have the third lattice. It's like these big hexagons.
Interesting.
Yeah. And now electrons, they feel like potential of this third lattice, new lattice.
So like for example on this picture here,
Yeah.
It's like the electrons are going to be like kind of wherever the white spots are, where like the purple ones are, or where.
Yeah, they just want to sit inside these hexagons.
Oh, okay.
So they create like some maxima and minima of electron density.
Okay, so it's like on this, it's like every single. Well, I was going to show this here. So it's like every single electron kind of wants to sit in one of these like little holes here.
Yes.
And it's like these are kind of like little walls, like of like a honeycomb, like kind of.
Yeah.
Okay.
And when you pour more and more electrons into this system,
Yeah.
they jump from one side to
Yeah.
another,
They're
trying
to
to
get
find
okay.
local minimum of energy, all that stuff.
I could see that'd be very interesting to study. So.
Second.
Okay. Yeah, it kind of looks like you got two there.
So here we have twisted part.
Okay.
So and then we can transfer it on top of some target
Okay.
substrate. It's pre-patterned substrate with electrodes.
Trying to look for something right now, or
I'm trying to show you pre-patterned substrate.
okay. Whoa.
It's a bit dirty because I didn't clean it.
That's so cool.
So
mean, just looking at it like like you can barely see it at all on here. There's anything here.
This area is like 100 by 100 microns.
So how did you?
Hmm?
Because so presumably like the different like the layers or like the colors are like transparencies, correct? For like how light reflects. How did someone go about manufacturing something like this?
You just need to know what color corresponds to certain thickness.
Okay. So you go, okay, I want these things, so you just have to like etch extremely tiny grooves at a certain like depth in to be able to get that. Okay.
Okay, and now we need to heat up our substrate even more. So use 180 Celsius.
Okay.
This temperature is enough to melt the first polymer, so I can release it,
Okay.
release my structure on the surface.
And you're gonna try and get the pieces of graphene to go like in that center part right there.
Yes.
Okay.
Now we can align it with
Okay.
target area. We need to wait a bit.
Yeah. So is this what's this graph showing right here?
So
I assume this is temperature.
this is current.
What?
This is just current.
Okay. So are they just like putting a current through here, just like
Yes.
okay. Well, Wally, I gotta ask.
Yeah.
What, like, when you were sitting in undergrad, you were like, learning all like the different physics things. What made you sit there and go, this is what's really interesting. I want to like work on like solid state physics. Why are you in this field?
I don't have a good answer. I mean, I don't know. I
Yeah.
don't know. I think it just happened. So once I attend some demonstration in National Research Lab,
Okay.
and I thought, oh, it would be really nice to try to do something like that. And I asked them to be like a lab assistant or someone else, and they agreed.
Oh, wow.
So I started when I was undergrad.
Okay. So, that's really interesting. So, just talking to people, a lot of people have very different stories on like how they got into their certain field. Some people, like I know I was talking to someone who's a graduate in physics, and they came in as like they were thinking about doing like condensed matter theory, and they went, this is actually isn't super interesting to me. I kind of like more practical sides, and I'm switching to like more experimental stuff.
Well,
Did
you can do that. I mean, maybe it's hard to switch when you already have your PhD.
Yeah.
It's hard, but if you do not have your PhD yet,
Mhm.
so you can switch.
Okay.
You can try experimental physics, theory.
Yeah.
So now it's already quite hot.
Okay. So, like the little wave patterns are showing that's like it's starting to come in contact, or
No, it's not contact right now.
okay.
We have close.
Okay. That's contact.
Now, yeah. Okay. Now we should wait a bit
Okay.
to let this polymer become more soft.
Yeah. So for this, the boron nitride polymer, like, when you like start working in this lab, I don't know if you know if anything about this, but like, how did you come about saying, okay, we need to have a way to be able to transfer graphene around? Did you guys come up with this method? Did someone else come up with this? Or
No, it's not our discovery.
yeah,
People did it before us. So we're trying to follow the best procedures, and
okay,
we are trying to improve them. I mean, you can find many designs of these transfer microscopes, and
okay,
you can think, oh, what do I need? How can I make my life easier, right? So, for example, here we have like vacuum holders for stages, for glass slides. I need to glue it with sticky
yeah,
tapes and all that stuff. So yeah, we just following the best procedures and trying to improve.
okay.
I think yeah, we reached the temperature, and now we can go back. So here you can
Okay.
see the polymer is creeping apart
Okay.
because we leave part of that on the surface.
Mm-hmm.
Okay. So, now our device is on the surface.
Okay.
So the next step is to clean the polymer using chloroform,
Okay.
and then it's ready for device fabrication. As I told, then we need just to fabricate contacts,
Yeah.
and we're ready to measure it.
That's a lot easier than I was expecting for you to be able to form something like that.
Yes, usually when someone talks about quantum materials, you
Yeah.
mention that it's crazy, complicated
Yeah.
growth in MBE or something.
Yeah.
But here it's quite.
Here, it took us 30 minutes to be able to create this whole thing. That's very convenient, very nice. So yeah. So then after this, you clean it, and then you would then like where would you bring this afterwards?
Well, yeah, I should go to clean room, our Notre Dame fabrication facility.
Okay.
I should use.
Oh, is that the one in Central
Yeah,
Greenwich?
yeah.
Yeah.
I should use a bunch of equipment to process that.
Okay. Yeah, I have a lot of friends who are taking classes in the clean room right now. Sounds like a lot of fun. It's just they talk a lot about it's like you have to be very clean to be able to enter there because you need to have a certain like dust count or whatever. It has to be like below or whatever.
Well, as you noticed, our structures are quite small.
Yeah.
So we don't care about dust because dust is like dust particles. They are too big. I mean, if dust particles comes here,
Yeah.
I would see it as like a giant blob. So our structures is too small for dust.
Okay. So, like, just to transport this, like, over there, would you just, like, put this, like, a little case and just bring it somewhere? Okay. Like one of these cases?
Yes, one of these cases.
Okay. So,
yeah,
and
maybe I even can show you the picture of
okay.
the device.
So like, what's an example of like a test you would run when you're in the clean room? Like what's a example of like what's something you would like want to test? Like we just like electric current through there, or like we trying to something out? Like how would you like what's an example of something you might run when you're in the clean room with this new like is it graphene moire called it?
Well, I cannot really test it in clean room.
Yeah.
I need to use some of our machines.
Okay.
This computer doesn't work well.
Yeah. Well,
It looks like it's not the best device.
yeah.
Like that. So we have contacts.
So how do you attach these like do you just like have to go in like a tweezers or how do you like how do you like is it the same process where you have to like heat something up and like move it on there or how do you get these contacts?
You mean contact to these heads?
Yeah, like these like wire
These wires.
yeah.
We use EBA,
Which is
electron beam lithography.
okay.
So we use electron beam to create like 1 micrometer wide trenches. And then we deposit metal.
Okay. Interesting.
This is the only way to do that.
Interesting. Okay. That's really cool.
Yeah, and then we put it into our fancy snow machine.
Okay.
And, yeah, we can investigate.
Okay. So like so now we've seen this next part. Let's look at this one like this is a turgioplasma cleaner.
Plasma cleaner.
So
Yeah.
what does this do?
Well, we use it to clean our surfaces of our chips and substrates to make them more sticky.
Okay.
So it's when you transfer something, you want to have as stickier as possible surface as not to lose your structure after transfer.
Okay. And then we got this whole machine right here with a lot of fancy gloves.
Well, this is so-called glow box. So
okay.
basically, this is just some box with inert atmosphere. So we have pure argon here, ultra high purity argon.
Wow.
And if you have some materials which are very sensitive to oxygen or moisture or whatever, you can do the same procedure as we did a few minutes ago here inside the glove box. And here we have this 3D joystick, so you can do X, Y, and Z.
Wow. So
I think our most fascinating machine is this one.
Okay, this looks like a large scaffolding thing, but I've learned quickly that's not the case.
So this is a scanning near field optical microscope.
Okay.
We have a chamber here.
Okay.
It's a kind of cryostat, so we can cool it down to like 8 Kelvin.
Okay. For our viewers who don't know, 8 Kelvin's about the temperature of space. So it's very, very cold.
I think our vacuum is better than in some areas of space.
Okay, yeah. So why would you need to cool something down that cold? Is that like...
Yeah, because temperature can destroy these interactions.
Okay.
So if your fascinating physics emerges only within like 10 milli electron volt range of energy, so at room temperature you have 26 milli eV thermal noise.
Okay.
It can destroy any coherent states. So you need to cool it down.
Okay.
And in this machine, the most interesting part of this machine is that here we can overcome Abbe diffraction limit.
Okay.
So we don't care about any diffraction limits. So we use metallized tip to scatter light from that tip, and we can detect it with detector. And our resolution basically equals to the size of tip. And our tip is very small, like 10 nanometers.
Okay.
So we can use 10 microns light and have 10 nanometers spatial resolution.
Wow.
Which is beyond any diffraction.
That's amazing. So that's like what, like wait, 10 nanometers would be like that'd be like 30 carbon atoms across
Yes.
or something. Wow, that's so small. So, and what's the rest of this like box for? Is this
Well, this is framed for some control boxes, lock-ins, current sources. So we are still building this lab.
yeah,
So 1 year ago when I came, uh, this room was just like empty and with square walls without anything. So we
okay,
built everything here for this year.
okay. So have you been part of like the build phase for this as well, like where you've been, or has that been more like other people working on like the actual building of this whole lab?
Well, yeah, general services, they helped us a lot to build like these rails and with wiring, with water, everything. Yeah, but what like we have to set up all the equipment. It's my
Okay,
work.
okay. So what are these rails eventually going to be used for?
Well, it's for some heavy wires. For example, for cryo compressor, we have quite thick metalized metal wires.
Okay,
It's like metal tubes
yep,
which supplies helium to our whole head
okay,
up here. So it's quite heavy, so we don't want them to just hang around.
gotcha. Okay,
I also have terahertz laser.
okay.
Nothing expensive.
So what would you use a laser for in like this lab?
So as I told you, we are going to study flat bands. And
Okay,
in flat bands, energy gaps, they're tiny. So
yeah.
they're like 10 milli electron volts, 5 milli electron
Mhm.
volts. And visible light, for example, is an order of like two electron volts.
Okay.
So it's
So you need to get a
too
thousand times
energetic.
small. Yeah.
Yes. I need very long wavelength and
Yep.
very tiny energy. So this laser can provide us with terahertz light. Basically, it's thermal radiation. So it's 118 micrometers. And
Okay.
10 millieV. So
Okay.
we want to use that laser.
And that allows you to do that's the range of energy for the flood band.
Yes.
Okay.
We want to study some plasmonics within the flood band. It's really fascinating.
Okay.
Yeah.
So, I guess before we, I got a couple final questions for you. Let's say you're kind of like interested in like something we learned today, you like solid state, or like maybe like learn about cryogenics or lasers, or anything else we talked about, like, and you kind of want to learn some more, but you're not like you haven't taken like graduate level classes in physics. What are some like recommendations, like things like just some like interesting things to like learn about, like kind of like more like a little bit more, like more base level. Like let's say assume you have like let's say you assume like you're an undergrad, you're like working stuff. Like what are some recommendations for you to like learn about?
If you are really interested in these things, you have just come and work.
Okay.
I mean, it's not. You cannot learn all this stuff in class.
Yeah.
You can learn some equations, how to solve problems.
Mhm.
It's very useful. It's very useful. But nobody is going to teach you how to operate compressor laser. You
Okay.
just have to come, have to work, have to listen to people who know how to do that, and you have to learn. That's the only way to know how to do it.
Okay. But you brought up an interesting, you talked about like equations in class. How much do you do math in like a lab setting here?
Not much, I would say,
Okay.
because you can solve some problem in class.
Yeah.
Because these problems has already been solved, right?
Yeah.
When you face like a real problem, very complicated problem, you have to be a physicist of really high level. So you
Yeah.
need to know better than your professor, probably,
Okay.
when it's real problem.
Yeah.
And you cannot do both like frontier experiments and like top level theory physics. You have very limited amount of time, and you need to focus on the field and approach which is the most interesting.
Okay. So, but if you, let's say, to go in like condensed matter, let's say theory, you'd probably be a lot more math heavy then if you're then compared to the experimental.
Yes, yes, sure. If you want to do theory, you should be very good at math, very good at quantum physics. You should solve equations. You should know how to multiply metrics and all
Yeah.
that stuff. So yeah, you definitely have to do that, and you have to work with great theorists.
Yeah.
You cannot do theory working alone in experimental lab.
Yeah.
It's well, you can, but it's not very efficient way.
Yeah. So how do you like? So do you? Are there like different like condensed matter theorists that you work with at
Yeah,
Notre
yeah,
Dame
sure.
to like?
When I face real problem, I usually provide with experimental data and my like phenomenological understanding on what's going on. But then some really good theorists can take my data and calculate something and say if I'm right or wrong.
Okay.
Yeah, you should work as.
So do they also help you with like designing experiments, or that's something you do on your own? So
Well, it depends. It depends. Sometimes I design experiment on my own, and then I ask them for help.
mhm.
Sometimes I can read some nice theory paper, and I can notice that nobody checked it or proved
Yeah.
it, and I can do that. So that's kind of works in both directions.
Okay. So like for example, like with like the graphene more what you're doing today, and we talked about like how like you said 1.1 degrees is that critical angle, like that magic number.
Yeah.
Did you like? I assume you probably didn't discover it. Someone else probably discovered it. Like that would that be like a? Is that something like you could theoretically predict? Like that, like a theoretician went up to an experiment and say, "Hey, try it at 1.1 degrees. That'd be a really nice number." Or would you say, or so you didn't try every single degree?
Well, yeah, it actually was like that because Alan MacDonald calculated that angle and told that 1.1 degree should be really nice choice because it seems like you can find flat ends.
Okay.
People tried and they found it.
Okay.
So, yeah.
Do you ever just like try just for, like if you have like, oh, I got some spare time, let's just try like 1.8 degrees and see what happens or something. Or
Yeah, sure. People do it all the time. I mean, I think in experiment it happens all the time. You just do something, you do not expect anything, and then you can see some phenomenon that you cannot really understand naively, and you start digging into it, and then it turns out that it's really interesting physics, and you can publish paper.
okay.
Sometimes it's just accident.
Have you gotten to publish a paper at your time at Notre Dame?
We already prepared one paper and sent it to publisher,
Okay.
but it's still not reviewed, so we have.
Okay.
We have
If you don't mind asking, what's the paper on?
this paper dedicated to launching of focused Fanon polaritons by sub-wavelength hexagonal Borodin tripresonators.
Okay.
We used our SNOM to reveal some new physics about Fanon polaritons.
Okay. Any other fun experiments you've done? Like, do you have like a favorite thing that you've done in the lab so far?
I think that this experiment that we are trying to publish is the funnest one. So I designed it. It's worked. It's cool.
That's truly fascinating. Well, thank you so much, Bogdan, for
Yeah, thank you.
interviewing and showing us all this cool stuff. So, thank you so much, and thank you to Professor Stepanov for like this whole lab and getting everything set up.
Thank you for having me.
Oh yeah, no problem. So, thank you so much.